spatial resolution. As far as satellite remote sensing is concerned, the most important thing is that one is the spectral values, the one is the spatial. Let us see about the spatial resolution. What is spatial resolution? So, we talk about satellites which are looking at the Earth's surface from an altitude of say 600 to 800 kilometers. Now, what is that it looking? It will be looking at, I told you, a part of the land, a strip of a land that could be as wide as 20 kilometers, 30 kilometers, 50 kilometers, even 150 to 170 kilometers of width. Now, what is that it is looking at? It is looking at different aspects, because when I talk about 170 kilometers by 170 kilometers, definitely it will be looking at various aspects, not only one type of land. Now, this spatial resolution is nothing but the capability of the satellite to decipher an object based on the size of the object. Let me put it in other words, the smallest size of the object which is discernible on a satellite image. In the sense, we talk about satellites are having a different types of resolution. I am talking with respect to size. It ranges from say 1 kilometer in the earlier days to 1 meter now. Just imagine. So, what is the resolution? The largest resolution now we have is 1 meter. In fact, it is lesser than 1 meter because of various scientific purposes. They normally release the data which has got a resolution of 1 meter. So, you know that it covers about 1 meter by 1 meter to 1 kilometer by 1 meter. So, that will be the spatial resolution of a satellite. So, you find that 1 kilometer, if you just look at the slide, you will get a better idea. This is 1 kilometer resolution. You can see huge land of India. Then you talk about 360 meters resolution, where you can see Tamil Nadu, a part of it seen here. Then 188 meters, 23 meters, 5 meters, and now it is 1 meter. I was just telling you, you see how beautiful the way in which the resolution has evolved, 1 kilometer to 1 meter. Now, we talk about satellites about 1 kilometer and 1 meter. Of course, we also have satellites which have got 1 kilometer depending upon the application. When you talk about something like the entire land, that is something like say a famine which is occurring in an area, or if you want to talk about the various forest cover in a given area, you cannot talk about or you cannot work on 1 meter. You should go for a much smaller resolution. When I say smaller resolution, the size of the pixel will be 1 kilometer, half a kilometer, or 383 meters depending upon the type of satellites. But when you talk about infrastructure, like I am interested in developing or working in a particular area, namely urban area, I want to map all the buildings which are present in that area. I can't talk about 1 kilometer because the size of the buildings are so small, I need to go for a 1 meter. So, depending upon the application, we decide what could be the resolution which I have to select. Then we talk about the spectral resolution. As you just see, spectral resolution is what is dependent on your wavelength. It is the width of the spectral band and the number of spectral bands which are available to mankind through various satellites. So, when I say width of the spectral band, I was just telling you about blue band, green band, red band, 0.4 to 0.5, 0.5 to 0.6, 0.6 to 0.7, then followed by infrared 0.7 to 1.1. So, satellites are designed in such a way, it will be having a specific resolution with respect to the spectral values, namely 0.4 to 0.5 or whatever it is that. Of course, depending upon the study which has been based on the earth or the ground study, they have decided to have different resolutions for different types of satellites. Now, here if you just look at the slide here, you will be getting a better idea. So, when you talk about various bands, I was just telling you that satellites will be having n number of say sensors, and it will be having different bands. You can see here band 1 of a specific satellite, do not worry about what is the type of satellite, 0.45 to 0.52 it is blue color, 0.53 to 0.6 it is green color, 0.63 to 0.69 it is red color or red band rather, 0.76 to 0.9 near infrared, 1.55 to 1.75 middle infrared, 10.4 to 12.5 thermal infrared, and then 2.07 to 2.35 is your middle infrared. You can also see that very important, it is not exactly your width of your blue band. I was telling you blue band is over 0.4 to 0.5, but you can see how it is overlapping a little into your say green also. So, 0.4 to 0.5 is the actual bandwidth of your blue, but it is also overlapping into a little of green. The second case, it is not exactly 5 to 6, it is 0.53 to 0.6. Then the third case again, it is not between 6 and 7, it is 0.63 to 0.69. What does it mean? So, we are just trying to say that irrespective of the bandwidth which is available as it is, we need not necessarily follow that one. So, based on the study on the ground surface, normally we call it as the general laboratory studies. So, we conduct a lot of research in the ground and then decide what could be the best possible spectral width which can be designed or which can be put on the satellite, so that it will be looking at the surface and capturing. Most of the satellites will have similar ranges, it is not that there will be a lot of variation. But of course, we have one particular wavelength, namely called as the panchromatic or pan, we call it as 0.52 to 0.9. You can see that how it is overlapping the entire thing with say 0.5 is your, I was telling you about green, and up to 0.9 that is near infrared. So, the entire range, and you can say observe very importantly there is no blue band required here. So, it is 0.52 to 0.9. Why blue band is not required, I will just tell you. So, we have a specific width called as your panchromatic. Panchromatic, as all of you know, is nothing but black and white. So, you cannot split the bands. Unless you split the bands you will not be possible to get color. Hence, we get if I combine a specific width, we will be getting what is known as your panchromatic. If you are splitting the bands in such a way, blue, green, red, we will be getting data in this form: blue band, green band, red, NIR, MIR, TIR and MIR, again this middle infrared. It is overlapping into the after thermal infrared. So, we find that if I have the blue band, green band, red band data, if I use namely color analogy, blue, green, red. Now, you talk about the color analogy, blue, green, red. You have filters which are blue, green, red. You have bands which are blue, green, red. If I overlap or put the filters respectively blue on blue, green on green, red on red, I will naturally get a true color. So, this is what is the concept or process of your color, where you get color photographs. But incidentally, when you just observe the thermal or the spectral signature, you find that blue band is not of much use, in the sense absorption takes place of the various bands once it is going beyond the blue. Hence, water bodies are the only ones which can be identified using blue band. Hence, over a period of time, they decided that blue band may not be useful for any kind of real application. Hence, they discarded the blue band. Now, what am I left with? I am left with green, red, infrared. Infrared again could be 3 different bands, or it could be 1 or 2 depending upon the satellite. Some of the satellites will have just blue, green, red and NIR. Some of them will have blue, green, red, NIR and MIR, and this particular satellite what I have shown you here is a Landsat satellite which has got 7 different bands, all of them blue, green, red, infrared in 4 varieties, as well as your panchromatic. So, depending upon the satellites, depending upon the requirement, we will decide which are the spectrums which are applicable for that particular application. Now, when you talk about blue, green, red filter, you will have a true color, but when I work with satellite data, as I find that there is a blue band will not be contributing much to the discrimination of the objects, we try to use only the green, red, infrared bands, blue, green, red filters. Obviously, when I am applying blue on green, green on red, red on infrared, the resulting image will be obviously a false color composite. Hence, the FCC, or otherwise called as false color composite, has come into vogue, and they have started using this effectively over a long time. Of course, you must be wondering what this gentleman is talking about false color composite when I am looking at the Google data which is in true color or natural color. Because in Google, they do not bother about the application part, they just work on what is present where, and they just try to apply blue, green, red and blue, green, red on your say the satellite bands. Let us see now how a particular type of, very important, underline this, how a particular landscape will behave with respect to different types of bands. Last class we have just seen that how the various bands, 7 bands which are available in Landsat satellite are present with different bandwidths. Now, let us see how it behaves with respect to the different types of objects in a particular given landscape. Here we talk about different types. One is a water body, sand, forest, urban and corn. So, we have the satellite, the energy which is being reflected by the sun which is emitted by the sun is reflected on these various objects, and it gets reflected, and I keep my satellite here and absorb that or receive that particular wavelength. It could be of different wavelengths. Let me say here water, as you see here, I was just telling you about the bands blue, green, red, NIR, blue, green, red, NIR. So, 1, 2, 3, 4 indicates blue band, green band, red band and NIR band. As you see here, blue, green, red, infrared, as far as water is concerned, it is dipping, and once it reaches NIR, it almost gets zero reflectance. When you talk about sand, it is invariably similar in nature. When you talk about forest, as you know, green in color, as you all know, blue less reflectance, green greater reflectance, again red lesser, infrared is huge or massive rather. Urban, you talk about blue, green relatively okay, when you talk about red and infrared it is lesser. Whereas corn, you talk about again a kind of vegetation where you find it will be less, better, poor and very great. So, this is what you should understand. Any given area, if you have different types of objects, please remember in remote sensing and GIS we use the word objects for everything and anything on the earth's surface. Any type of object here, water, sand, forest or urban, we say that different bands behave or receive different reflectant energy. So, we will be interested in knowing which part of the energy is reflecting more, and that energy is only being absorbed by the or which is being received by the satellites. Satellites receive the energy on its way while passing through the stations which are normally placed on the earth's surface. It dumps the data, and that energy we receive and the process the data, and finally we use it for our application. So, let us see how the energy is stored. So, I have just showed you or explained you have different bands and different objects how it behaves. Now, I should be capable of storing the energy, isn't it? Or once I receive energy, how do I receive, how do I store the energy? So, we say what is called as radiometric sensitivity. That means, what is the sensitivity of that particular object to differentiate or capability to differentiate the spectral reflectance or emittance from various targets rather. Naturally, we talk about the most important thing, the quantization levels within the spectral band. To what extent it can quantify the data. So, quantization level means to what extent these energies are quantified based on the reflectance. If it is green color object, green and infrared are reflecting, others are absorbed. So, you know that the energy which is reflected, energy is one, namely your sun's energy, but object is the same again, but it is in different wavelengths. So, each of the wavelength behave differently. So, we try to quantify or quantize the data, the energy in such a way we should be in a position to understand what is the extent of reflectance. Let me put it in simple words. Say, if a body or object is capable of absorbing 100% of energy, then the reflectance is 0, isn't it? When a body or object is capable of reflecting 100% of energy, then absorption is 0, reflectance is maximum. So, somewhere we have to understand what will be the value in which it is doing. So, we need some sort of a mechanism so that I will be quantifying the value. I can't just say absorption and reflectance, I should also be capable of quantifying the data. So, that is where this levels of your sensitivity with respect to various wavelengths with respect to the objects will come into play. Normally, we say that the intensity levels or the maximum capability of the object to reflect the energy. So, when you talk about intensity levels, we also call it as gray levels. Why do you call it as gray levels? Simple example let me give, so you will be in a position to understand that. Objects which are capable of reflecting will obviously be white in color. Objects which are absorbing most of the energy will be darker in color. So, if you take into consideration that particular aspect, let me say, if I mention any one particular object on the earth's surface which is capable of reflecting 100% of energy, just for example, could be snow, isn't it? Large ice caps, snow will be reflecting maximum energy. Similarly, when I talk about absorption, of course, you can also think when I am telling you about this, absorption, we say that tar, or we call it the bitumen, which is dark in color, which is absorbing the maximum energy. But incidentally, on the earth's surface, we don't have objects either which can absorb 100% or reflect 100%. Hence, we say that all objects on the earth's surface are otherwise termed as gray objects. That's why reason we call it as intensity levels or gray levels, and how it is obtained. Because we are using computers, we talk about the bit levels. 0 to 63, 6 bit, 0 to 127, 7 bit, 0 to 255, 8 bit. Naturally, 0 to 63 totaling, have you thought of it? It is nothing but 64, 128 and 256. It is nothing but 2 power, just tell me what could be the possible, 2 power 6, 2 power 7 and 2 power 8. So, that will be the value 0 to say 63, 0 to 127 and 0 to 255 levels. So, when you talk about 8 bit level, invariably of course, you also talk about 32 bit and 64 bit computers now, but still as far as remote sensing is concerned, they consider only 8 bit level. That is more than sufficient. You talk about 8 bit and it will be 256 levels, and we try to say that 0 represents dark black or your absorbed energy, 255 or 127 or your 63 represents white color reflecting energy. It will be maximum 100%. As I just told you just now, you don't have any object on the earth's surface which is either 100% capable of reflecting or absorbing the energy. Hence, all of them are called as say gray objects. And we normally store the data converting the energy into say digital number. That is what I just told you about 0 to 255. That means any object, if it is reflecting energy, that electrical energy is converted into a digital number. That could be either between 0 to 255. As I told you, 0 is not possible, 255 is not possible. Depending upon the wavelength, depending upon the object on the earth's surface, it could be 100, 30, 40, 60, whatever could be the value. So, that is what is your radiometric sensitivity. In summary, let us see what exactly how the remote sensing instrumentation works. I am just telling you about the energy which is falling on the surface, and energy is reflected by the objects, it is being collected, and you have a satellite will contain what is called as a recorder, receptor or detector, and it passes through as usual a routine processing or image rather is captured as an image, not as a photograph, and it passes through this lens and then it is recorded here, and that energy converted into say digital number, and it is passed to the surface or sent to the surface once it receives it passes through your say the receiving stations. So, you find that different satellites will be going in different orbits, and as it comes over the country which has launched the satellite, it will be dumping the data, and you find what is called as the ground trace and repeat. So, you will be in a position to trace the details, and you will be in a position to acquire or get the data from that. So, over a period of time, you will find the satellites will be covering the earth's surface and will be dumping the data as and when it reaches or passes through your say receiving station, ground receiving stations. So, the satellites are also tracked rather. So, anytime you should understand, isn't it? Satellite should not be losing its path, whether it is going to be geostationary or your polar orbiting. Either of the satellites will be controlled from the ground, and they will be in a position to know what is the exact track and the path. Normally, we say the path of the satellite, that is you will have what is called as a calendar. Over a period of time, they say that from day 1 to day 365 in a given year, the satellites will be passing this particular area. So, we have what is called as the path of the satellite. So, this path calendar will be helping us to know which satellite is passing through which part of the land surface. Of course, there will be so many constraints in getting the data. Some of the satellites are normally shut when it is passing through other countries. For example, when you talk about our India, we try to shut the satellite when you are passing through some of the neighboring countries, and whereas some satellites will be trying to capture the entire earth as it is. So, they do not bother about which area they are passing through. We collect the data from the satellite in the form of say digital numbers, and that will be collected or received by the receiving station. In India, we have what is called as your NRSA, National Remote Sensing Agency, who are actually supposed to receive the data, and they will be storing the data in some. Let us see about that, and that's what is our main topic, namely your image processing. I just told you, satellites do not photograph the Earth's surface, it only images the Earth's surface. So that will be in the form of, say, digital numbers. It reaches the Earth's surface, and from there we will be in a position to understand or work with the satellite data. Of course, there are other so many constraints or details what you should also just get an idea. Invariably, satellite data is of two different types. They are either radiometrically corrected or geometrically corrected. We will see the details a little later. Depending upon the kind of study, if an individual is interested in scientific understanding of how this data behaves with respect to various objects, he will have to work on, say, the radiometrically corrected data. He collects the data and then studies that. If an individual is interested in understanding what is present on the Earth's surface, maybe most of us will be working on that, namely called as application scientists or engineers, who will be working on what is present where on the Earth's surface. In that context, we will be using, say, geometrically corrected data. In either of the cases, it has to be done by an agency which is not within the reach of a common man. It is done by Government of India, especially I was just telling you about National Remote Sensing Agency or NRSA. This is located in Hyderabad, India, and they will be receiving the data from various satellites. It is not that they receive the satellite only from Indian remote sensing satellites, they also receive from various other countries. There is satellites which are launched by various other countries like Spot satellites, the French government, or the United States satellites, namely Landsat series. Any kind of satellite, whatever is passing through, we have to procure the data. As far as Indian satellites are concerned, we will be getting throughout its lifetime, whereas other satellites we have to procure the data by making a payment and just request them to say that at this particular time, this particular day, based on the calendar I told you, the satellite path and path calendar, we will be knowing during which period of this time this particular satellite will be passing through India, and we can request them and they will be providing the permission and we can download the data. But some of the satellites which are beyond the scope of the government agencies are being operated by private operators. So in that context, we will not be in a position to receive the data directly. There are other agencies who receive the data, pass it to the individual only through Government of India. So it is not that we can get a data directly from any of the private flyers. So they will not be in a position to give the data to us directly. They will send the data through NRSA, and only from them we will be in a position to acquire the data or use the data for our any kind of application. So I was telling you what exactly you are going to work and what exactly you mean by remote sensing, how you will be getting the data. You see here, whether it is going to be aeroplane, as we will be seeing at later stage how aerial photographs are taken and what is the importance of aeroplanes, or it could be satellites. In either of the cases, we find that the data will be in this form. I just told you, digital numbers covering an area of could be 170 kilometers by 170 kilometers, or it could be 10 kilometers by 10 kilometers or 30 kilometers by 30 kilometers. Irrespective of that, so for example, if this is 30 kilometers and this is 30 kilometers, this entire area is split or divided into n number of cells. Simple method of splitting depending upon the spatial resolution. I told you about the resolution or the cells. So when I talk about spatial resolution, if it is going to be 1 meter by 1 meter, let me take for example 1 kilometer size by 1 kilometer. That means I will be getting 1 meter by 1 meter cells for the entire 1 kilometer by 1 kilometer, isn't it? So when I talk about that, I say 1000 cells here and 1000 cells here. That means 10 power 6 will be the number of cells will be obtaining for 1 kilometer by 1 kilometer, say your resolution, if the resolution is 1 meter. If the resolution is 1 kilometer, what will happen? The entire area is covered in one single cell, isn't it? So you should be deciding what could be the possible application and what is the required resolution. So as you see here, this particular area, let me presume that I am working on 1 meter, I will be having n number of cells here, n number of cells here, and the total area will be covering 1 kilometer, about a square kilometer. Depending upon type of this object. If the size of the object is greater than 1 meter, only then it will be capable of reflecting, or in other words, the energy what is reflected by this 1 meter by 1 meter is the average energy which is within that 1 meter. If the object is much lesser than 1 meter, you may have more than one object here, and obviously this area 1 meter by 1 meter, it will be reflecting the average reflectance. If you talk about objects which are larger than 1 meter, say the entire area is one single object, then obviously for every 1 meter you will be getting data of the same object. In the first case, it was average of all the objects within that 1 meter or 10 meters, 100 meters. The second case, you find that it is all one particular object reflecting the energy, and the reflected energy is obtained by us. So, what we are supposed to get, we will be getting for one single band data this many number of cells. If I have 4 different bands in the satellites, obviously for the same area I will be getting 4 different data. So, that is the crux of your remote sensing. So, what is important here? If I have 1 kilometer, there is no issue. If I have 1 meter resolution, even for 1 kilometer of area, I will be getting 10 power 6 number of cells as far as your satellite is concerned. But at the same time, if I am going to use 4 bands, 6 bands, 7 bands, for 1 kilometer you will be getting millions and millions of cell data. So, it is going to be a huge process, isn't it? Receiving the data, storing the data, and processing the data. If it is going to be larger size, not a big issue. If it is going to be small size, I was telling you 170 kilometers the size of the swath, or say even for example 50 kilometers. 50 kilometers by 50 kilometers, imagine the total volume of data which is received is 1 meter resolution. With 1 kilometer or 100 meters, 20 meters, 30 meters, not an issue. Because 1 meter, huge volume of data is received by the receiving station, and it has to be stored in a proper format. That is what we normally do as far as say remote sensing is concerned. As we come back to the slide here, what we tend to do is that we try to get the data in digital numbers. So, the satellite will not know what exactly it is looking. What it knows is that object, reflectance, and that energy, whatever is the value between 0 to 255, if it is a 8 bit. So, whatever is present here, its reflectance is recorded. So, the data is received, and then we decide what exactly we are going to do with the data. So, once the data is received by the receiving station, we have to process the data effectively.